on two generators. First generator for focusing of ultrasound and second generator in the room 408. In the first part of our laboratory work, we should focus ultrasound, because what is ultrasound? It is propagation of mechanical waves in any medium, in air, in the water, in soft tissues, in bone tissue. Frequency of ultrasound is more than 20,000 Hz. And ultrasound is the usual wave. And so ultrasound can be focused in any point. We can focus it using special glass with focusing bottom. Bottom of this glass like lens, concave lens. But why concave lens direct our ultrasound in this point, not in this point? Because you know that this lens, like my glasses, should direct rays in this direction, not here, but this direction should be here. Because here this glass we fill by water up to this label. Then between the bottom of this glass and surface of radiator, we put or Vaseline or any water or another medium, coupling medium. Because if we have a small layer of air, this layer will absorb all ultrasound oscillation, and ultrasound not pass in the second medium. We can explain focusing by the Snell's law. You know this law from school. Sine alpha over sine beta is equal to V1 over V2. Alpha is incident angle, angle between ultrasound rays and perpendicular to the point of refraction. Beta is the angle between perpendicular and refracting ray. V1 is velocity of ultrasound in the first medium, glass, and V2 is velocity of ultrasound in the second medium, water. Because V1 is more than V2, then alpha will more than beta. This angle should be more than this angle. In the point of focusing, we have or fontaine or aerosol, and we have heating. We can check it if we put thermometer in this point of focusing. And we have in this point aerosol and big fontaine and heat of this tissue. Ultrasound can hit, focusing can hit biological tissue, rats for example, first experiment, on 100 and more degrees. But in physiotherapy, it is only 2-3 centigrade degree. Heating is very small. And in the last experiment, we use another glass with parallel walls. Here we have parallel labels. Distance between these labels 1 centimeter. Then we put this label on radiator of ultrasound transmitter, and we see these labels. Parallel labels on the screen. Then we put here water and starch, and we put on transmitter. We have here standing wave. In the nodes of standing wave, we have collection of particles of starch. Distance between two particles, two lines of starch, is equal lambda by 2. We measure on the height h, on this height, we measure how many these halves 1, 2, 3, 4, and so on, 10 on the edge. We have, for example, 10. 10 times lambda by 2 is equal to this height. From here, lambda is equal to h over n. And lambda is very small, 1.6 millimeter, 1.2, depends on medium and frequency, very small. And because lambda is very small, yes, все время что-то идет и идет, туалет, наверное, хочет. And we can show ultrasound like rays, not like the wave, but we can show like ray, because very, very small wavelength. To find velocity of ultrasound, we use this formula. Velocity is equal product of lambda and frequency of generator. Frequency of generator is given 880 kilohertz times lambda, and we have approximately 1,500 meter per second. Very high frequency in the soft tissues and in the water. In the bone tissue, approximately 2,000. Velocity of ultrasound depends on density. More density of biological tissue, more velocity of ultrasound in this tissue. 1, 2, 3. Next.